Okay. What happened? Oh, this is interesting. Okay, well, I guess it really doesn't matter. So today we're going to continue with the high frequency response. And Wednesday we're going to look at the low frequency response. And then, so by that time we finish chapter 10, frequency response part. And then next week we're going to start the following chapter on feedback, switching to another important topic. So if we look at what we started this week, let me give you a brief review because we have our quiz on Wednesday. So hopefully you're doing your homework and then you know what to prepare for. We start talking about capacitance, how it worked, and then how the high frequency is being attenuated with this simple low pass filter. And we draw the body diagram, and we look at the gain, we look at the time constants, and we look at the upper gain and things like that. And then we moved on to talk about the high frequency response, how this your low frequency portion gets attenuated because the circuit is a CR circuit. The reason is always because the impedance of C is 1 over omega C. So when omega is big, 1 omega C becomes 0, right? So that's why you got this. But in the previous circuit, when C is big, when omega is big, on this one, C becomes 1 over omega C becomes 0, your output becomes 0. So that's why the high frequency gets attenuated. When the frequency gets to a certain point, you don't have any output. And then in MOSFETs, because we have plates, we have connectors, each gate, drain and source, we have metal. So between metal, we have capacitance. And those capacitance can be expressed between each of them, they're very small. So that's why in the previous chapters, we never consider them because they're so small that we neglect them all the time for the middle band. But when you design your amplifier, if your frequency in the middle band, you don't have to worry about it. But if your frequency is very wide, and some of those will be attenuated, and you have trouble. You're gonna have trouble. You know, for example, when you amplify a music, when I say something with this microphone, and it gets amplified, if the frequency band is so narrow, only portion of my voice gets amplified, and you will hear a distorted voice. In a symphony, you got a frequency goes from low, like hertz, up to kilohertz. But if your frequency band is only in the middle, you might not hear everything. You only hear part of the things that's amplified, right? So that's why we are concerned by this frequency at this stage. So for each of these capacitance, they impact the circuit, and we basically control the small signal equivalent circuit. In a small signal equivalent circuit, you have VGS are now used to be open circuit. Now you have the CGS connected between gate and the source. Typically, this CSB between source and the base, and also between drain and base of the MOSFET, which base is this big part, they're typically very small. So for the frequency ranges that we are normally working with, we can neglect those. But in some applications, in the extremely high frequency, like in the tens of gigahertz or hundreds of gigahertz, you know, up to very high frequency, you have to consider this as well. Because that's 1 over omega C, because the omega is so big, even C is small, it becomes something, right? So you have to consider. But for those typical applications, we can neglect them. That's why in this book, we neglect them. Okay? But if you consider them, but still, you see, this is just a circuit. If you learn 2 times very well, you can solve the circuit. And you can look at the gain. from input to output, that's why we do simulation, because as this gets more complicated, it's very hard to do analytical analysis. That's why we need to do the simulations. So, but in this book, to give us idea how this impact of a frequency response, we neglect the train to base and so on, and we solve for this circuit. When we solve for this circuit, we have two ways. One is we solve for the short circuit. Current gain is called AI, like current gain. And then we can solve for the common source amplifier to get the voltage gain. That's A lowercase v. So then we can have input output impedance, and we can solve all of that. So we neglect with CBD and so on. Here we solve for the short circuit gain. When you have a short circuit gain, you can see eventually this output gain is something here. What you can see here is that the GM is the middle band. And this is a high frequency gain. When this omega becomes big, this started to increase. So where we have this frequency, which we call the transition frequency, if you use this by divide by 2 pi, you get the frequency. This is the angular frequency in radians per second. Divide by 2 pi, you get hertz. And this is what you get the transition frequency. And then we can plot this curve. Well, the FT is over there. So for short circuit, you get one frequency is FT. That's FT is important. In the quiz, you're probably going to solve something like that. So we calculate FT. So that indicates your short circuit current gain is constantly below that FT. At FT, you got 3 dB attenuation. Above FT, your frequency goes up and your gain attenuate 20 dB for every decade of frequency increase. So from 100 hertz to 10 kilohertz, from 10 kilohertz to 100 kilohertz, and so on for decade. So that's the short circuit. And then we went on to, so for the BJT, and then same thing, only difference is that now we have R pi. In the MOSFET, there's no R pi, right? So that's the only difference, but the performance is essentially the same. And then we went on to look at the common source amplifier. For the common source amplifier, we look at the open circuit voltage gain. Now we have this RL. This RL is a combination of RL and the internal resistance RO, the early resistance, and we solve for this circuit. In order to solve for this circuit, we did some approximation because the CGD is quite small, so the current through CGD is very small. So we normally can neglect the current in order to get our insight to look at what really it does tell you. So it's kind of looking inside what happens. So you can do this simplification just to give you a better idea how this system works. So that's how we neglect current, but we still look at the current response, and then we derive it, and we derive the output through this process. Eventually, we get the gain, and I believe we have the gain that, we calculate this CEQ by neglecting the current between these two, and we got the CEQ derived, and then we got the gain. So in the gain, well, you have this, basically, this is the middle band gain, because when S is small, this is 0. When omega is small, this becomes 0. So this is the middle band gain. When S increases, at some point, you got this point. This is where you have omega equal to 1 over this number, which is here. This is called 3 dB, because at this frequency, this is 1 plus 1 is 2. So your amplitude, 1 plus 1 J, okay, it's not 2, it's square root of 2. So 20 log square root of 2 is minus 3. So that's why from here, you minus 3 dB, that's your high frequency cutoff frequency. So FT and FH are different. FT is the transition frequency, that's for the short circuit current gain. FH is the voltage gain. We use this quite more often, okay? FT is not normally used. So in your quiz, you should be able to calculate FT and FH separately. Okay, so that's what we're going to do on Wednesday. So we get this voltage gain, and then we also went on to look at what happens when RSIG is small, because that doesn't happen quite often, but sometimes you could have something to that degree. So then when we neglect it, we can calculate the circuit, and eventually we get a gain like this. And this is the middle band gain, right? And then we get our high frequency gain, which has something that's very interesting, is instead of pole, pole is something below the equation here. This is the pole. Pole is omega equal to 1 over CL plus CGD times RL. That's your pole. But you also get a 0. You also get a 0. 0 is on top on the numerator. So you get a pole, get a 0. And for the pole, which is here, FH, which is again your cutoff frequency. But once you get to the pole, see, your gain is no longer decreasing because the pole cancels and it becomes flat. Now, to be honest with you, we don't really care about this region because that's really the gain is already so small. We normally don't use it, but just for the concept-wise, you do have at some point your gain is no longer going to decrease, but it actually keep a constant. So in theory, you can use this part as an amplifier too, but just your gain is very small. That's all. Okay. So that's what we did last week, and then apparently you can do the same thing for the common emitter amplifier, which again, the only difference you got R pi, and then you do the same thing. You do the same simplification to get CEQ, and then you can derive the gain, and you can get the same cutoff frequency for high frequency cutoff frequency. You get this point. So this is very critical. So if you really you want to get the gain is where this point is very important, is 20 log. If you look at this voltage gain equal to -3, that's what you have for that point. So 3 dB is what you get for that gain. So this is corresponding to your FH, which is your high frequency cutoff frequency. So by this point, we also did well because we did a little bit by the Miller's theorem, because what we found is what the capacitor between gate and the drain, or the capacitor between base and collector was quite difficult to simulate. So that's why we have this Miller theorem. We don't use that quite often. So we're going to skip section 10.3, 10.5 for now, and then we're going to go over to the high frequency response of differential amplifiers. But before I get to that point, let me talk about just a little one thing here. So far we have talked about the high frequency response. And what you might want to ask, like one of the students come to my office, okay, why are we doing this? And what does it mean? Well, what really happens is that when you get a MOSFET device, you want to design your amplifier. So what happens is that you need to know your frequency of the signal of your input. Again, with this sound amplification as an example, your symphony comes in with all different instruments. You have a bass, you have a violin, you have piano, and you have this, all these different instruments. Each of them will have a different frequency. So if you select your amplifier, but that frequency band is so small, you're going to lose a lot of information, right? So when you design it, you need to calculate what's your highest frequency you want to amplify. That is where you need to design your FH. It has to be above that. So if it's too low, you lose information. It's no good. So you need to design your FH is like at least 1 decade, we call, above your desired frequency band. So this will work. This will work. Now, by Wednesday, we're going to talk about low frequency response, which means if your frequency is too low, it also is going to attenuate. So this middle band is where you want your circuit to work. Now, sometimes your frequency band is so big that you cannot even enlarge your frequency band to cover everything. So now you need to understand, well, what's happening to my high frequency? So my middle band gets amplified, but my high band gets attenuated. How much is it attenuated? If it's attenuated too much, the information is lost. But if it doesn't attenuate so much, it still works for you. So that may be okay. Okay, that's one thing. Another thing is every system will have noise. Yeah, we're going to touch a little bit today as well. You don't want your noise to get amplified, right? So sometimes you say, oh, why don't I just go buy this device and this circuit that has very wideband frequency so that I don't have to worry about my signal being lost? Well, for one, that device is going to be expensive because the narrower the band you have, the cheaper. The high precision device, yes, it works, but it's expensive, right? Do you want to spend that kind of money for your system? And secondly, when you have such a large band, you might accidentally amplify some noise that you didn't want. So if you is here, but the noise is here, you want that noise to be attenuated, right? But if you design your circuit with such a large band, okay, here, yes, it gets amplified, but the noise also gets amplified. Now you have trouble because the noise is also there and here. That's why for this like a voice, like microphones, it's very important that you design your frequency right, that you hear the voice, you don't have noise. But sometimes you go to some sort of performance, something, you will see the people adjusting amplification here. So what happens, that noise gets amplified. And then that maybe you want a feedback, let's pick it up. So that you don't like it, nobody like it because that the noise was so terrible that they hurt my ears, right? So that's why this frequency band is so important that you have to be careful. It's not the wider the better. It has to be right. Okay. Yeah. So so that's the kind of thing. Now, so far, so we talk about the common emitter amplifiers that and the common source amplifiers. If you want to go to the common gate and the common drain, which is in the book, you will see the performance is pretty much similar. All it does is that these capacitors, the junction capacitors, they impact your high frequency response. For low frequency, because again, if you write this everything here, so for omega is small, and this becomes 0. For omega is big, and then this is started to be something. Okay, so and then today we're going to talk about the differential amplifiers. So this is our typical amplifier, and the circuit is simplified. So in the sense that you have Q1, Q2 as a differential pair. For the differential pair, of course, later on we're going to talk about you have common mode input. You can also potentially have a differential input, okay? And here we use this QS to represent a current mirror. So think of this as a current source. So you might say, okay, what's the thing with current source? Well, with current source, really, this can be written as like a current source and resistance. So this resistance is what we call RSS. This is like I reference. So that's a really just difference between this. You can transfer to here. So in the middle band, we didn't worry about something else. We only worry about this, right? And but then in the high frequency, you see what happens? This will have capacitance. Remember, this has capacitance between here. It has capacitance over here. So typically, you might have capacitance over here too, right? So basically, we can represent this capacitance, we call CSS. So we have this CSS represent the overall capacitance of this device. So now we can replace this whole part of the circuit with this, right? So now what you're seeing is, okay, we have this, and then at the top, of course, is this two amplifiers. I'm not going to draw it here. You know what it is now. From differential amplifier, we just learned a couple of weeks ago. When we have this differential input, do you still remember what happened with the current source below that? For differential input? Because for differential input, the current goes this way for small signal. Therefore, the bottom part over here, it doesn't matter. So it's all gone.
for differential amplify. So regardless of what I draw here, it does not impact my high frequency response. That's for differential input. So for this one, only this one, right? So that's one conclusion. So for differential input, the current source that has intrinsic impedance and resistance, it does not impact my differential gain. But for common mode input, the current goes this way. However, if the common mode input is perfectly matched, if it's perfectly matched, exactly will be half here and half here, and your output is still 0. So therefore, it still doesn't matter. Okay. So you might say, okay, well, so what are you talking about? It doesn't matter. Well, since what happens is that in the common mode, if the device is not matched, that's where the problem comes in. Remember, when the device is not matched, we do have a common mode output, which is proportional usually to the parameter mismatch. That mismatch, because of resistance mismatch, you have a common mode output. The ratio between common mode output and the differential output is called, do you still remember the term? Yeah, common mode rejection ratio, which is defined as differential mode and common mode. And we use this. So if your common mode gain is 0, in the matched case, your common mode rejection ratio is infinity, which means there's no common mode to worry about. But if your common mode input, common mode gain is not 0, but something, and then we have to worry about it. So now we're going to look at what exactly happens with the common mode and with this one here. But before I do that, I want to draw the half circuit for the differential gain. So the half circuit for the differential gain will be for the small signal circuit. So if we look at this over here, you might already know that, well, this is exactly the same as the common source amplifier we just got, right? So if you plug in the capacitors, the resistance, everything, yes, you will get exactly the equation that we get from the common source amplifier, which means we're going to get this. We're going to get this. This is your FH, and this is your frequency. That's your 20 log AV. Okay, this is your 3 dB is right over here. Okay, so that's what we have for the differential gain. And then we know that the differential gain for the middle band, you know, it's going to be GM times RO or RD. This RO is the resistance of this transistor. That's the middle band. And for the differential okay. So this is where we draw the circuit for this is the differential input, and this is the common mode input. So for the common mode input, we now have to consider the resistance and the capacitance. So now this is the half circuit. So in the half circuit, remember we double the resistance before. Okay, but now we divide CSS by 2. So why don't we double? Why do we divide it? Well, because impedance is 1 over omega c, right? So when you're splitting them, you doubles. That's why you'll see your resistance doubles, but your resistance divided by half. So this is a common mode circuit. So for the common mode circuit, before the RS, so before adding CSS, we have this common mode gain minus RD for 2 RSS This is what I mean before. Is before we add RSS, it's a common mode gain. Common mode gain is related to RD, third RD or RD, that's only one. Remember, we talked about a few things. The R could change, the transistor could change, and the gain could change. Everything will result in some equation similar to this. So it's like a sensitivity. If you third RD, the third RD is the difference between the two RDs. Between the two RDs. So if your third RD is a 0, which means they're perfectly matched, your common mode gain is 0. And your common mode rejection ratio is infinity, okay? But typically it's not possible. The RD always have some difference. That's when you go by 1% resistance, your maximum possibility is 1% difference, okay? Okay? So this is common mode gain. So since this is our common mode gain, I don't have to spend extra effort to derive what is the impact of frequency response, because I can simply get this part to be equivalent. So which means I draw this part to be an equivalent ZSS. And I replace this one with the SS. So I calculate ZSS is the parallel of 2 RSS in parallel with CSS over 2. Well, CSS over 2, the impedance of CSS over 2 is going to be okay, let me rewrite it. So CSS over here, we can write ZSS equal to 2 RSS in parallel with CSS over 2. CSS over 2, the impedance of CSS over 2 will be 1 over S CSS over 2. This S is the omega, right? So this is in parallel. So we can further write this into 2 RSS times S CSS over 2 divided by 2 RSS plus 1 over S. Oh, this is 1. Okay. S CSS over 2, and we can further multiply this S CSS over 2, and then we can get we can further get our SS over 1 plus S CSS RSS. So I got it right. Okay. So I got the impedance of ZSS now. So I would now plug in this one to the equation over here. I get 2 RD over 2 times ZSS times dirt RD over RD. So if you plug in this one into here, you will see that basically this becomes, because this is ZSS here. So let me write actually to give you idea to see what it means. Something's wrong. Right. Okay, that's fine. So, and then let me write down this ACM equal to minus RD over 2 RSS third RD over RD and over 1 plus S CSS and RSS. So this is your common mode gain. I can write 1 here. So this common mode gain has this one. You see this one is exactly the middle band. So which means if you look at it here, what happens is when the frequency is small. When S is small, what happens?
Once it's small, this is 0, which means this is your middle band. But when S increases, what happens with the common mode gain? It increases, which is good or bad? Bad, because you don't want your common mode noise to be amplified. So that's bad. So that's why we got a frequency of this one here. For the 3 dB frequency, you can write down as what they call it. I call it F0 because it's 0, but this is like for CM, right? So it's going to be 1 over 2 pi times CSS times RSS. So this is your 0 at this frequency. So this is bad because your common mode gain start to increase. So in theory, when you design your amplifier, what you need to do is you make sure your FZ for CM is more than your frequency band that you're using. So if it's not, which means your noise is gonna increase. Okay. So when you guys designing the simulations, you can try different parameters, and you can see how your common mode and the differential mode is going to change. Now for the simulation, so apparently when you put up 2 RDs, they're going to be the same, right? So what you can do for your common mode, you can click on one of them, like put 10 kilo ohm, for example, another one put it 10.1, right? So now you can see the common mode output. So this is very easy to do in simulation. In real life, they're always different, but in simulation, you can manipulate the numbers to see the output. And then you can see the frequency, right? So by one stage, when we talk about low frequency, and now you have the whole picture, you'll see, okay, well, this is going up, and low frequency is attenuated. A middle band is good, up band, and you can start to change the capacitance, and you can see how your frequency band decrease and increase and decrease, increase. And so it's very interesting when you do the simulations. You can change the parameters. So in this case, we have this this gain. So let me get this SEM. Yeah. So we have CMRR equal to A differentiable O to CM mode. So now you have your differential mode. Let me go to my equation here. So, and you have this for the middle band, you have this GM times RD, but then for the high frequency band, let me see what it is. We have yeah, we have this one GM. Over 2 times no RD over 2 RSS. Okay, RD. Maybe here is one. Rewrite it. Okay. So GM times RD is your middle. I'm looking at the middle band right now. So RD over 2 RSS times third RD over RD. So this RD is going to cancel. So you have 2 GM RSS over third RD over RD. So that's your that's in the middle band. So as we already know, the better the CMRR, the better your system. So therefore, to increase CMRR, we can increase SS, we can increase GM, and we can decrease. We can decrease this ratio, which means this last one indicate is the better resistance, the better, the higher the common mode rejection ratio. So when you go to DGK, for example, when you buy a resistor, you're going to see a huge difference. You're going to buy the 5% resistance and maybe like 1 cent each. If you buy 1%, it might become 20 cents each. If you buy 0.1%, it become, I don't know, $3, $4 each. So that's huge difference in terms of that. But the high, so in the common mode rejection section, we also talk about sometimes what happens if there is actually a difference. You can design for DC offset. Remember, we try to design the circuit so that we can bring that circuit to compensate your parameter differences. So that's why for good electronics designer, they can use cheap components, but they can still design a good amplifier. So for beginners, it's hard. So we always use the expensive component to design a bad amplifier. Because the problem is with a good amplifier, the bandwidth is so big, the noise and the signal, everything gets amplified. So that's why you think you can get a good amplifier circuit, but it's not, because everything gets amplified. So it's not good, actually. So it's very important. So if we draw the circuit again for the middle, let me draw this. So this is for the FH. This is your, let me see if I have, actually, so this is actually better. So this is your, this is the one that we talk about for the CM. Remember earlier I didn't draw CM, but your CM started to increase to this point. But at some point, of course, it's going to level off or even decrease, because we have not talked about other things in the circuit. But we're simply talking about the CSS. The circuit actually has other component. We're going to look at later on today. But this is where you have to pay attention, is your common mode rejection ratio is, not rejection ratio. Your common mode gain is a constant value at the middle band, but it started to increase, which is not good, above this FZ. So think about our, if we draw our differential gain, and if our differential gain is something like this, so this is our FH. So if your FZ and FH, they don't, ideally, what do you think for FZ and FH for these two circuits? Ideally, this number should overlap, because that means your middle band gain, common mode gain is constant, is small, and your middle band differential gain is the largest. So that would be nice. But in real life, it's difficult to design these two together. So what happens is that either FZ is smaller than FH in this case that I draw, and or it could be have another case. I mean, it depends on the circuit. So if I get my CMRR, my CMRR, you see what happens between not zero, but this logarithm. So between this point and this point, my common mode gain is my AD over ACM, right? So that's a constant. So from here to here is a constant. So what happens at FZ? What happens after FZ? My AD is a constant,
but my ACM start to increase. What happened to the common mode rejection ratio? It's decreasing linearly. So it decreased by 20 dB. So it's decreasing. Okay. And what happens at FH? Because you have decreased 20 dB per decade and increase 20 dB per decade. So those two are going to cancel. And it's like you have something at the 0, something at pole. So basically you have 1 plus S omega omega 0, 0, and then you have 1 plus S omega pole. So you have this. So when S is at SFH, these two cancels, and maybe this is called H. So these two cancel, then you have this constant. So if I enlarge this one, so basically it's like this. And this is your FZ, your FH. So what effectively is that because your FZ is lower than FH, so you effectively reduce your usable middle band by the difference of FZ and FH. If these two overlap, it would be good because you're virtually extending your middle band. Okay? But what happens if your FH is smaller than your FZ? You can basically draw the circuit similarly, but that's rare. Mostly your FZ will be smaller than your FH because the CSS, if we go back to the circuit, you will notice why, because your CSS is the total resistance of this one. So if I draw the circuit, what it means is that you have this MOSFET. So SS is the capacitance of this one plus the capacitance of this one. So this is CGD, this is CGS, right? And you also have a capacitance of this one, C like a DS. Normally, again, this is small, so we neglect it, but that's the total resistance. That's why, total capacitance. So that's why your omega Z is always smaller than your omega H. So that's what we have. Okay, so I think I already have enough explained. And then you want to look at, yeah. Okay, so in the case that where we have like this is interesting, because that FZ in fact is not, it's gonna, the CMR is gonna decrease and then ACM increase, but it's only to a certain range. It's gonna flat out because other capacitance start to kick in that we did not look at, and we're not gonna look at it because it's too complex. But what we want to do is we want to move on to this circuit over here to discuss just a little bit what really it means to have a circuit, well, the common mode rejection ratio makes a big difference. So this is a very typical multi-stage amplifier, like we talked about in the last chapter. So the multi-stage amplifier has a stage 1 input, is Q1 and Q2, and the output of Q1, Q2 is a differential output. And the differential output is given to stage 2, which is made of Q3 and Q4. You can see the input coming here, and the input coming here. And for each of this stage, you have a current source. So in theory, you will have RSS and CSS at each stage, right? So in fact, you could, ideally, you can also draw this over here. And then you can also draw the capacitance over here, capacitance over here, and capacitance over here, things like that, and so on. So You control all the capacitance, everything. So all these capacitance are internal to the devices, and they make a huge difference at high frequency because they start to show impedance in your circuit, right? So in this example, the book briefly discussed, I thought it's very interesting, is that they said sometimes in a power supply, VDD, you have a noise, and which is true. If you go to our lab, when you guys do any experiment, 330, 430, whatever, you look at any power supply and you use your oscilloscope to measure the DC. If you use a multimeter, you don't see it because it gives you a number. But if you use an oscilloscope to measure the DC voltage, when you have a Yosef straight line initially, but keep increase the reduce the time scale. Keep increase the time scale, and you will see it start to have some noise coming. Those noise are coming from many sources. Some of those are coming from the power supply itself. For example, 50 hertz, 60 hertz, because you rectify 60 hertz, so that coming in. Some coming from like environmental noises, and some like interference from other circuits in the room. Pick it up. That's high frequency. And sometimes because if it's not a linear power supply, you have a switching power supply, and those switching frequency gets picked up. So those are the noises. And you will see noises like this. Some of them has a regular frequency, like a 60 hertz noise, you can see it. But for some high frequency noise, sometimes they call it white noise, they pick it up from the environment. Some other switching devices, lights, these days we all have this LED lights. The LED lights use power electronics, they use switching power supply. Those switching generate the noise. We don't hear it because the frequency is high, typically in the hundreds of kilohertz, but it can be picked up by a receiver, something, okay? So those noises coming in, the voltage, it is picked up by this. Because VDD has a noise. Even if RD no noise, I no noise, but this VDD minus this one, the noise is coming here because VDD has a noise. And that noise is on top of the DC, very small, typically in the millivolts. Your voltage is say 5 volts, 10 volts, 12 volts, whatever, right? Your noise is in the millivolts. However, the problem is that our typical small signal is also in the millivolts range. Okay, that's the problem, right? I don't care 5 millivolts to my 5 volts, it's only like a 0.1%, not a problem. But if it's picked up by your amplifier, it's comparable to your input. So your input is a few millivolts, it's picked up. Okay, and then this gets amplified. So here, which means at this node, if you measure it, if you use, okay, now, oh, the other thing I forgot to explain. When you measure DC voltage, right? You see a DC 5 volts and you keep increase the range, you increase the scale, you're gonna see it. But if the scale is too big, it runs out of your screen, you cannot see it, right? Then use AC. Your oscilloscope has a DC measurement, AC measurement. Use AC measurement filled out the DC. Okay, the DC is gone. You only look at AC. Now you can increase your time scale, decrease your time scale, and increase your amplitude scale, and you can see the noise coming. So if you measure it over here, you're going to see the noise. Once that noise coming in, it's amplified over here. Once that noise coming here, because you have this resistance and capacitance, that noise, yeah, that noise becomes even further amplified. If that is further amplified at your output, you see what happens? You get a signal, yes, but you get a bunch of noise. If that noise has a frequency similar to your input signal, you're in trouble. You don't know what it is because yours is overlapped. But if your input has a frequency which is much lower than the noise, you can still distinguish because what you get is going to be something like this. You're going to get something, let's say this is your input, and then this is your output actual signal you want. If the frequency is really high, the noise, you got something like this. In fact, any amplifier, any circuit, if you zoom in enough, you see this. Okay? It's the ratio. If the ratio is so small, we don't care. Because if we get what we want, we don't care about the noise, right? I mean, I'll give you an example. If everybody talks in the room, but with very low voice, everybody can hear what I talk, it's okay. But if your voice is so big that they can only hear what you talk, not me talk, or they hear mixed, and then that's trouble, right? That's the same thing in amplifier. If the noise is a small percentage of your actual signal, it's okay. But if it's comparable to your signal, it's going to be in trouble. So that's why it gets amplified. And then we have now what you need to do is we can design the circuit such that we can potentially reduce or even almost cancel the noise. So that's the key. So for this, we need to go back to our other section that we learned about the DC offset, how to compensate DC offset. That's how you do it. So by introducing a little bit offset, on here, that you can attenuate the noise, but only amplify the signal you want. Okay, so this is for the two stage. And next, we're going to talk just a little bit on the current load. If the circuit. So before, when we talk about the circuit before, we had a resistance load over here and a resistance load over here, and we do have something over here too. But you see, we talk about the resistance is something we don't want to make in integrated circuits. We always wanted to use a current source as a load, which increases the resistance by itself. The intrinsic resistance RO is big, which is good. And also, it's easy to make a transistor than to make a resistance on an IC design. So therefore, if you look at the integrated circuit design, you always have some current source as a load instead of a resistance. But if you have a current load, see in this particular example, of course, if you can make up the circuit, you would also have something for the common mode. You can add a current source here, right? So you can do that. But for this one, really, what it boils down to is this. If I draw the half circuit for the small signal, this becomes ground. But for the common mode, it becomes, this is what we have from the last, just we talked about. And here you have for common mode, you have this, right? So this is your RO3, your RO3, this is RO whatever, this is RSS, okay? And this is CSS. And then from this circuit, we can start to draw this, we start to draw this, and then we start to draw this resistance RO, and so on, right? So for this, you have all this. Now, for this top resistance, for this top one, you will have, okay, so for the top one, you're going to have, let me draw on this diagram here. So for the top one, you're going to see also resistance, capacitance, like from gate to source, from here to here, like this one here to here. Okay, so this one, of course, you have here to here, you have here to here. Right. So now, what you can see from the top is that the two capacitance, they're kind of in series, right? So in the book, what they did is, okay, so there's a capacitance, equivalent capacitance. We're going to take everything together, we form a CM. Okay, So that's kind of the total equivalent capacitance of the upper circuit. And then for this one here, we're also going to have the capacitance, but we're going to take them all over to use a CL to represent the second stage, the future capacitance, right? So then we are going to have this equivalent circuit. We have the CL, and yeah, so here you have this capacitance. So if you want to draw the equivalent circuit for this one, for example, you can draw here. I just want to and you can draw the circuit and then you have this CM, and this your CGS, this your CGD, and this your GM times VGS, and this your RO1, and this your RO3, and this your CM. So this circuit, very simple, because once we draw the small signal circuit, and this two are in parallel, and actually this is also in parallel. So this all this in parallel. And then this one, we can do the analysis based on what we did before. Remember, we can neglect the current and then do a CEQ or use the Miller theorem. We can do the capacitor here, then this two become parallel, and then we can do all the circuit analysis. We can get all the gains. So once we get that, we can derive. Yeah, so this is where this is the output side. They have the CL, which is this one here, to get the analysis. And in the book, they tell you how much each capacitance is composed. For example, this is CM. Let me write down this too. Just give you idea. It's not important. You don't have to memorize these equations, but just to give you idea what they are consisted of, so that you have, oh, okay, this is what I mean, right? So this CM is equal to CGD1 plus CDB1 plus CDB3 plus CGS3 plus CGS4. So this apparently is the resistance, the capacitance of mostly Q3, like CDB3, GS3, GS4 is that one. And then this part of GD1 is this one here. So they get all this capacitance into CM, and they also have CL is written as CGD2 plus CDB2 plus CGD4 plus CDB4 plus CX. This CX is the next stage. So CX is the next stage because every stage has a capacitance, right? So in this case, once they write this, they can start to derive the gain. So for the gain, we know that the voltage gain is VO over VID. For the middle band, this is GM. This what is really copied from the previous lecture is we get the gain of the whole circuit, where this RO is equivalent of the RO and the other things, and then this is CL. This RO is the resistance for Q1 and Q3, internal resistance. So we can write RO as RO1 in parallel with RO2. 3, and this GM equal to GM1 equal to GM2, okay? So that's, we got that equation. So from here, you see there's one pole over here for CL. There's one pole. So basically, I think, let me see if there's actual diagram. Yes. So the diagram you would draw is like something like this. This is your FH over here. But then if you get the CM, plug in, this is a set of derivations, quite complicated. You know, I don't think we're going to have time to go through that. But the idea is that you get a 0. And when you get a 0, the 0 and pole would cancel. So when you have a pole, the gain start to decrease. When you have a 0, it cancels the pole. So you become the flat. So the things that we're interested really in here, I mean, even this pole, this 0 is not so much what we are concerned about because this is already beyond what we talk about. So what we really most concerned is still at this point. So that's why for this circuit, it's important to look at how CM is calculated. Let me write down the final equation just to do some analysis so we know what it means. So A equal to, this is GM times RO. And this RO equal to R01 parallel with RO3. So I just want to write the final expression because this tells you a little bit about something. Here you have 2 poles and 1 0. If you look at the 0, it's interesting because the 0, the term is CM over GM times 2, right? So which means the frequency of that 0 is it's half of the frequency of the or twice the frequency of the pole, right? So and you have here is 1/2 GM pole here, and then you get a 0 at this part. So that's the final output of your circuit with current mirror load. What again? Most of the time, we are just looking for this. What happens over this area is not so much important because that's beyond our calculation. But the key is to get these numbers to find out where they are, because these are going to determine how your amplified circuit works because this. So let's say if your FZ is not here, is here. Now you're going to have trouble, right? So you're going to have positive gain and up and then down. So typically, when your circuit has a gain increase, your amplifier is not stable. Okay, we're going to talk about that when we go to feedback control. Because the reason is that every noise coming in, it gets amplified, and it gets amplified, it gets amplified, your circuit eventually will be saturated. So you don't want your circuit to have a positive this dB increase. So that's why your FC has always to come after this FP2 in this case. But of course, in the previous example, that's a little different. If we go back to the circuit that we have here. Yeah, so over here, we want our FC to be before the FH. If it's up below FH, this is what we talk about the common rejection ratio, which is still going to be fine because we're going to control our FH, you know, typically below. So what this does is that this FZ, because our initial bandwidth is up to here, with FZ, it effectively reduces our bandwidth, which is not desirable, but it's okay. The circuit is going to be still stable. If your FZ is above your FH, we don't care because that's beyond our applications, right? So I think that's what I'm going to cover all of it today.
And then we're going to, let me tell you. So we're going to skip section 7 again. It's too much to teach or too much to learn. But the idea is that if you master one method, the others is naturally flow. Mathematically, it's very difficult because they got very complex. But the theory is the same. So eventually, what you need to do is do simulation, right? So when you design your circuit, but now you understand the principle. So when you do your simulation, you understand what it means. Because otherwise, if you don't take this class, you go to build a circuit, you have no idea what is going on here. Why is up? Why is it down? Why is much this much, right? So that's why. So, and then next week, next week we're going to talk about chapter 10, but Wednesday, we're going to talk about low frequency response. We're going to finish this chapter, chapter 10, right? So next chapter is chapter 11. Okay. And then for the simulation, for the projects, do you guys have any questions so far? So I know you guys already did something in 330, so this should be straightforward. So the only thing I'm asking you to do is to understand the frequency response. You know, in 330 you don't look at frequency response, but here you need to look at the frequency response. To look at frequency response, you have two methods. One is you apply AC signal, you set a frequency, and you look at the output. You change it from 1 Hertz, 10 Hertz, 100 Hertz, 1K, 10K, 1 meg, 1 gig, and you can look at your output. You're going to see your frequency, your output started, the sine waveform start to small and increase, and then decrease. So now you know that in the middle band. But it's hard to know where exactly this thing is going to stable, right? So that's why you need to do frequency response sweep. Sweep means the circuit is going to do simulation for all the frequencies for you, and it tells you the ratio between output and input. So you can set your frequency band, like the sweeping range from, let's say, 0.1 Hertz all the way to 1 gigahertz, and you can see your output. But if you don't have your capacitors connected, it might not give you the middle band. It might give you a flat line. So you know that your circuit does not have any capacitor unit. For example, if you take an IDEA device, MOSFET, IDEA device, no capacitance, it's not going to give you the high frequency band drop. But in that case, you need to use an extra device. Or if you use the IDEA device, you can manually input CGS and CDS, okay? CGD and CGS. So also for the BJT, it's CB, CBC and CBE, okay? So you can input those numbers. And for the low frequency response, of course, you have the external capacitance. You can try to change the capacitance, and you see how your low frequency bands start to change. Okay, so those are the interesting things you can do. Okay, that's all for today. Thank you. What is it? We just do a hybrid pi model. You do a pi model? Yeah. No, don't do pi model. You do the actual drop that. Yeah, I mean, if you do pi model for your own benefit, you can do it. Yeah, you can compare. But for your actual project, you have to do actual device.